Hello, my name is Ian Bentic. Today we'll be going over the proof of why the supremum of a upper bounded subset of the reals is unique. Let's begin. So here we have our assumptions. Here E tilde is a subset of the real numbers, and we have at least one supremum here. So supremum is any element in the reals. It doesn't necessarily have to be in our subset E tilde. Moreover, it is an upper bound of E tilde. And if gamma is any other element, then if it is less than our least upper bound, which is y1 tilde, then there exists some element in E tilde such that gamma is less than, gamma is less than x. So there is something in x or something in E tilde such that x is greater than gamma. So gamma cannot be an upper bound. So this is saying that gamma is not an upper bound, given that here gamma is less than our least upper bound. So this is a statement of the least upper bound. This is a statement that y1 tilde is an upper bound. So an upper bound, and then nothing can be a least upper bound other than this one. Okay. Here again, we have a similar statement where maybe we have another upper bound, and it is the least upper bound. The English sort of gives it away what we want. We read this in English as this is the these two statements together are read as the least upper bound. Okay, but that kind of beats us to the punch, so to speak. We are kind of analyzing this a bit further in English than we would in, say, the formal analysis. Okay, so that's the end of our assumptions here. This is the statement that the reals have an order on them. So there's an order on the reals, and I believe that any sort of order on the reals is isomorphic to any other order on the reals. So the usual way in which we describe this order is the subset notation, but I will not go into this in this video. Just know that there is an order on the reals. And specifically, we are using this property, which I put in here. This is our generalized AND notation, so we are just using AND elimination here. Moreover, we are substituting for x and y, a y1 tilde and a y2 tilde, which will take, and I see here I made a mistake. So it's always good to catch those little mistakes. And then since we know that y1 and y2 tilde, these are part of our assumptions here, so it is perfectly acceptable to use the modus ponens to derive this, which is our generalized exclusive OR. So we will be using a sort of an extended disjunctive syllogism. So we will use disjunctive syllogism twice to sort of remove these two statements here to reduce the statement down to this. So indeed, this extended exclusive OR notation means that exactly one of these situations must occur. Moreover, exactly one of these situations must occur. So if we eliminate this situation and that situation, that this situation must occur. Likewise, if we were to eliminate these two situations by proof by contradiction, we would end up having this. Okay, so let's continue. So we, again, like we said before, we have to assume one of these statements here. So we assume essentially this statement here. We are opting to use the usual way in which we use the order, where this is sort of a very formal way of saying this. So we allow for this convention to occur. Continuing on, we see that we highlighted this in purple. Where is this coming from? This is coming from here. Oh, actually, yes. So this, we are substituting in for gamma a y1 tilde. And this checks out. All good in the hood. As they say in formal mathematics, all good in the hood. That is a very formal way of saying that this is a completely valid deduction. All good in the hood. And then modus ponens, obviously this is our antecedent, this is a consequent, so on and so forth. And then we see here that we have an existential elimination argument proceeding. So here we are instantiating x tilde for x, because we love to keep those tildes above, so we kind of see everything. Could have used a letter, some other letter. However, we continue on, and then we are just using and elimination here. And then we see we go to our gold statement. Our gold statement is the statement that y1 is an upper bound of e tilde. So here, and indeed, we have that. But then we reach a contradiction here, because y1 tilde is less than x tilde. So here, this is the same thing as saying not y1 tilde is less than x tilde. Recall by the law of trichotomy, which is this essentially, that exactly one of these situations must occur. Either x is less than y1, or y1 is less than x, or x is equal to y1. Since we have this or statement here, this statement suffices for this statement. They are equivalent statements. And I'm not sure if we went over that in another video, but you can trust that if exactly one of the three situations must occur, that if we have potentially two situations must occurring, then surely one of these situations must not occur. Okay, and since we have these two statements, which are clearly a contradiction, we are allowed to use the usual way in which we end proof by contradiction for existential elimination, which is to using our explosion rule to say P and not P, and then we bring that here. Since there are no instances of X in P, not that I can recall, there's very little room to have an X in the P, and it is not a predicate, so it's just a sentence. So P and not P, we have P and not P again. Oh my goodness, another contradiction. So surely we can, then we just want to be a little formal with the tildes. We love to put our tildes over everything. Tilde, tilde, tilde. Okay, and essentially this is a similar argument. We are saying, okay, we go back to the green statement here. We're putting y2 tilde for any instances of gamma. Remember, this is gamma. Gamma kind of looks like a y, but it's not. It's gamma. It's a fun time. Okay, we go back here. Then we have, oh my goodness, another existential argument to use and go in the similar fashion. So this is like a real life example of W log, or without loss of generalization, because the argument is almost exactly the same, almost exactly, because we're just switching y1 and y2 for all the instances here. That's what we mean by without loss of generalization some of the time. I'm not sure. I'm not that good of a math student to know if this is always the case, but basically it's such a simple idea that we're just changing it over. We're just putting y2 here and then y1 over there, and then have basically the same argument occurring. So I won't go over it again since we went over it in the previous lines here. Okay, and here we have two statements, two negations. And since we must have one of these situations occurring, we must have exactly one of them. We've gotten rid of two of them. We've gotten rid of two. So we'll actually highlight these sorts of things here. We'll highlight this one in blue. Okay, well, it doesn't really highlight perfectly, but you get the point. Okay, this will be our blue statement. And here will be our, what should we give it up? Maybe a nice rose. It's a rose. Doesn't really look like rose. More like orange. I'm quite sure. But here we have another rose. Then we'll have this statement here. Look, I love giving things colors. We'll make it, ooh, nice. Maybe make it gold since it's like the main thing we're worried about. Give it a gold. So we just cited generalized disjunctive syllogism since we're basically crossing out two instances here. This is saying no, no. So we've gotten a no here. Oh, a no here and a no here. So we must have this, which is this one here. Okay. So now we have, okay, these were our assumptions before. This is not an assumption. Everything after this is not an assumption. All of these are assumptions. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, those are all assumptions. So we have a rule. We've made a new rule that if we have all these things here, for any subset of the reals, that if we have two upper bounds with this property, which makes it the least upper bound, so the English, again, sort of gives it away. Oh, this is the least upper bound. Because when you read it, let's try to analyze why we read this as least upper bound. This is saying for anything less than y1. Anything less, we know that y1 is an upper bound because it says here that if x is an e, then y1 must be greater than x. That's saying y1 is an upper bound. It's bigger than anything in x, or bigger than anything in e. Then we have this gamma. If gamma is anything smaller than y1, if it's anything just a little smidgen smaller, anything smaller, then we're always going to be able to find, this is saying we will be able to find an x and e such that gamma, which we were hoping would be an upper bound, but it's not an upper bound, is less than x. So this means exactly that we cannot have an upper bound, that gamma is not an upper bound, because there's something in E that is bigger than gamma. If gamma were bigger than anything in E, then it would be an upper bound. But this is saying that there's something that in E that is bigger than gamma. And this gamma is, here by assumption here, is less than y1. So anything less than y1 cannot be an upper bound. And again here, if y2 is an upper bound and it is the least upper bound, this is saying least upper bound again, then we're going to find a similar instance. And so we must have y1 is equal to y2 by this entire argument here. Now, if you have any other questions, maybe some of the notation is a bit finicky, I implore you to look at my other videos or ask questions in the comments or email me. My email you'll be able to find it in the About section. But yes, I hope this gave you sort of clarity as to the step-by-step procedure for how this actually all works. I know this is a little bit slow, and maybe in English it would make more intuitive sense, and I would agree with that. But I am a very scrupulous person, and I really like to type out things and make it hopefully less obscure. I actually find these things less obscure than natural language proofs, because you can actually see the sort of step-by-step justification. I know that I used some conventions, but these are the usual conventions, rather than saying this ordered pair is in this relation, or this order. An order is a relation, by the way. Like, this is, I hope you can forgive me for this, but yeah, it is, this is all fine and dandy. So now you can sort of take a look at it all. Maybe I will have like a PDF version of this in the about section, or not about section, but underneath the video. Maybe I'll put it in there so that you can sort of read line by line. And a good exercise you can do is sort of maybe write this out formally. I mean, if you've already shown this rule holds, this exclusive, generalized exclusive or, what do we call it? Generalized disjunctive syllogism for exclusive or. Maybe you can show that. That would be a good exercise to do. Maybe you could find that in a logic textbook. I'm not sure. Or maybe you could write down some of the steps we've done a little bit quickly, because this is actually 2 steps where we are using for all. There are some liberties we sort of go over quite quickly. Well, some people might think it's not so quick still, but what else can we sort of look at in this proof? Yeah, if you're not familiar with exclusive, or not exclusive, existential elimination, basically what's going on is that we know that something in E tilde, some x satisfies this property. And I'm pretty sure we call this when we put this here, this x tilde, it is called a witness. So we're using x tilde as a witness. It's like bringing it to the stand. It's like, what's happening? X tilde, tell me what's happening. And you have to, and x tilde is on the stand, and he or she or they must confess what is happening, and this is a confession, and whatever happens after this confession must hold, and an absurdity holds. So maybe x tilde is not a very reliable witness, but that's okay, because we get this, and that's how we usually end existential elimination proofs, with a proof by contradiction. Okay. Anyways, I hope it is quite clear what is happening. Maybe we'd like to write out the proof format. Proof format. 1, we acknowledge the order on the reals, and maybe I'll say this one, this fact here. We're using this fact. And then what are we doing? We use disjunctive syllogism, which is, okay, what is disjunctive syllogism? Which is disjunctive syllogism, like, well, not without the exclusive or, is this. So we have an argument, say we have an argument, A, B, and we have neg B, then we must have A. Or, okay, this could also be A, B, B. Okay, yeah, I'll write it like this, because otherwise, we could also write it like this. A, B, B, wedge, B, and A. And then, okay, these are basically 2 different ways of saying the same thing. This is I forget exactly how this works, but well, I actually do remember. I just don't want to explain it. But you can think of it like this. You can think of it like that. But we're using the extended version because we have 3 statements. So 3 statements. What would be an 3? So A, B, 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 C, wedge, neg, B, wedge, neg, C, A. Okay, so A here is actually, okay, maybe I should have done it by C. So maybe I'll do neg A, neg B. So you can kind of have a sort of matching. We have these 3 things. This is maybe the A statement. This is the B statement. This is the C statement. We have, okay, well, maybe I'll add more. I like adding. I always love to add more. I always think more is more. More is more. Sometimes more is less, or sometimes less is more. But okay, so basically, if we have 3 things here in this, these are not the same statements, by the way. These are not the same. This is just a rule. This is just a rule we use, and it's a logical rule that you can derive from logic. It's fun to do that. If you're really smart, then you don't have to think about these things. But if you're like me, you're a little slower than the rest, and that is okay. It's okay to be a little slow because personally, I think if you're a little slower, I just consider that you like to take your time to think. And I really love to take my time to think. So here. So this is the rule. And then use disjunctive syllogism. We could say twice or use the generalized exclusive or syllogism, or exclusive or syllogism. Which again is it's this one. It's this one. We have then not A, not B. What is our not A? Not A is this one. Not B is this one. And then we end up with C. It's like, because remember, one of these must occur. And I know I'm repeating a lot. And sometimes it's okay to repeat a lot to drill the point in your brain. Sometimes people just say one and done, but not me. I love to repeat things. Repeating is good. It helps you remember. And I would really suggest you to copy this down on a piece of paper. Paper is always better than typing it out. Yeah. And maybe if you know your logic rules, like how to write them down properly, maybe you can expand this out, expand this statement out in the proper way. I won't tell you what proper is. You can find that out later. Maybe I'll have another video for that, for an extended exclusive or, and then the subsequent syllogisms or logical rules that we can use to deduce things. I love to deduce. 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 Okay. So, okay, we're continuing this proof format. Okay, acknowledge that the order. Okay, I don't like that. The order on the reals. Okay, we use disjunctive syllogism twice, okay, and then we have derive that the supremum of a subset bounded above is unique, which is this statement: y1 is equal to y2. That's really this statement. If we have, so let's read this again. For any subset E that is in the reals, and it's necessarily bounded above, like it is bounded above by this statement. And we have 2 potential bounded aboves. They are bounded above by y1 and y2. So we have 2 potential candidates for the least upper bound, but using these properties here, using a combination of these properties, oops, this one and that one, we can derive contradictions. Okay, derive contradictions, get a not A, get a not B, which is the not A is a negation of this and not B is a negation of that. And then we get y1 equals y2, which is here. And we're done. All right, so I'm just going to put a, or maybe black box, I'm not sure. Box, does box work? Okay, no, not actually. Okay, so that's it. That is all. That is really all. Okay, well, I hope you enjoyed watching me rambling through. I know I like to watch me ramble through. So you have a great rest of your day and happy studying. Okay, bye. Bye, everyone.